Welcome to Presentation 37. Today we're going to talk about the infrared IR receiver and transmitter sensor module. The IR transceiver is part of our layer 3 architecture. We're going to be using the display capability from layer 3, and also for all our programming we're going to be using the UART framework, SPI framework, time counter framework, and I/O ports. The agenda for today would be as follows. First, I'm going to give you a description of the IR receiver and transmitter. Next, we're going to talk about the Sony protocol. And the reason we need to talk about the Sony protocol is because we're going to be using the Sony remote control as one of our source of IR transmission. Next, we're going to go through 3 sample programs, and finally we'll go through the summary. So let's start with the description. So I'm going to be talking about the IR transmitter, the receiver, and then I'm going to be talking about why we use a 40 kilohertz frequency, which is the frequency that we're going to use for all our IR transmission. So here we have a picture of the IR transmitter, and it basically connects to the microcontroller via the DAT pin, and then it has 2 pins for voltage and ground. Now the receiver is same. It has 1 line for the data, and then we have to provide voltage and ground so it works. This is the transmitter, which is an LED, and this is the receiver right here. So let's start talking about the transmitter. So it's just a regular LED, but it gives off infrared light. To send data, it flashes at the frequency of 40 kilohertz. Think of it like sending a Morse code, but instead of short and long beeps, you use a burst of 40 kilohertz lights. And I'll explain later why kilohertz. Now the receiver. The IR receiver is a small sensor that can see IR light, but only when it flashes at a 40 kilohertz frequency. Now, when we connect the receiver to the microcontroller, we're going to get 2 kinds of inputs from the receiver. And it's as follows. When it detects a valid 38 kilohertz signal, it will pull its output low. When there is no 38 kilohertz light signal, then the output stays high. So now let's see why we use the 40 hertz signal. Sunlight and lamps produce IR light continuously, which would cause noise. Using a specific frequency makes it easier to separate real signals from noise. Think of it like tuning a radio. Only one station comes through clearly. So next, let's talk about the Sony protocol. Like I noted, we're going to be using the Sony remote control as one of our sources of IR signals. So infrared remote controls have been around for a very long time now. Each manufacturer designs its own protocol. So when you take you buy different TVs and use the control remote, you have to understand that each manufacturer has its own protocol for its remote control. Now the signal is the same at 40 kilohertz, but the protocol is different. So let's look at the Sony protocol, which is what we're going to use. So the Sony protocol sends message can be of 12 bits, 15 bits, or 20 bits. Basically, either you buy a control remote that only is 12 bits or another control remote that sends message of 15 or 20. So that's why not all remotes work or Sony work on all Sony TVs. Now, if you look at the message itself, the 12 bits, you're going to always be interested in bits 0 through 6, the 7 bits, which is the command, and then it has some additional information about the device. Now, if you look at the 15 bits, again, you're going to see the first 7 bits, the command, and the same is for the 20 bits. So no matter what signal, what remote control you're using, if it's Sony, you have to get all the bits, but you're going to be just interested in one command. The command changes according to what button you have pressed. Now let's look at the signal. So the signals are going to be in multiples of 600 microseconds. So what I mean is that it's depending whether it's a 0 or 1 or the start. So you'll have a message going to start followed by zeros and ones. So no matter what you're getting, it's always going to be a multiple of 600 microseconds. So let's see what that means. So first we're going to have the start message. Always when you get a message, the first message is going to be the start, which means, hey, data follows. And that's going to be 5 times 600 microseconds. Then a logic 0 is going to be 2t. And finally, a logic 1 is going to be 3t. We have it here. So let's see what that means. So if they're going to send you the start message, then you're going to have a signal which is on for 2400 microseconds and is off for 600 microseconds. So I have it here, I show it, a 2400 microseconds on and 600 microseconds off. Now let's look at how they send a 0. A 0 is going to be 600 microseconds on and 600 microseconds off. You can see here a 0 is on for 600 milliseconds and off for 600 milliseconds. So let's look what a 1, how a 1 is represented. So a logic 1 is going to be represented by 2t, which is 12 microseconds on and 600 microseconds off. So this is a 1, so it's going to be 1200 microseconds on and 600 microseconds off. And basically that's the Sony protocol, and that's what we're going to have to decode. So let's look at the sample program 1. So what we're going to do on sample program 1 is we're having our microcontroller is going to be hooked up to the IR receiver, and also it's going to be hooked up to the laptop. The idea is that we're going to send message. We're going to press the button for the remote control 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, and we're going to get the message, and we want to decode it and send the data to the laptop so we can figure out what commands go with each of the numbers. Now, as far as the IR receiver is concerned, we need to measure the duration of the signal, so we're going to use input capturing to do that. So look at the program statement. So read the signal being transmitted by the Sony remote control and determine what are the commands for buttons 0 through 9. Use the input capturing to characterize the signal. Output all data to the laptop via the serial interface. So let's go ahead and see how we're going to go about doing that. To characterize the signal, we're going to use the input capturing capability of the microprocessor. And these are the steps we're going to follow. Number 1, we're going to set the interrupt to trigger on the input signal falling edge. Once the interrupt triggers, we're going to record the time of the event in the variable start tick. After doing that, we're going to reset the interrupt routine to trigger on input signal rising edge. So first we set it up from falling edge. Now we want it to trigger on rising edge. Once it triggers on rising edge, we're going to record the time on the end tick variable. Now, to get the signal duration of that event, we're going to subtract the start tick minus the end tick. Once we've gotten 12 bits, then we're going to analyze the message, because the message is 12-bit message. So let's look how we do that portion. So we're going to get into this interrupt routine with either we had a falling edge or a rising edge. Either of those two events are going to trigger this particular interrupt. So we need to know if this interrupt was triggered by a falling edge or a rising edge. So the first question we ask is, hey, is the edge, was it a not rising, which means a falling edge? And if the answer is yes, then first thing we do, we store the data, the time when this happened on the start tick. Then we change the edge to rising, and then we modify the interrupt so it triggers on rising edge. So that's this portion. Now, when we go back in, what's going to happen is we're going to go to the else, because now we set up the edge variable to say rises. So this is not going to be true, so it's going to go to the else. So once it gets to the else, it's going to record the time when this happened, and then it's going to subtract the end tick minus the start tick and store that message. So we can analyze this once we get the 12 bits. Now I have here an if statement, because we don't know if the clock that measures the number of tick has rollover. So if the end tick is greater than the start tick, then we know that the clock hasn't rolled over, so this is fine. However, if the clock has rolled over, the counter, I should say, not the clock, then we need to do this particular formula to figure out what's the duration of the signal, which is going to be 16-bit clock minus start tick plus the end tick. Now, once we do that, so once we store the duration of that particular bit, then we go and say change the edge to not rising, change the interrupt to trigger on falling edge, and then we increase this inhibit. What this is going to do is figure out how many times we've store message duration on this particular array, and once it gets to 12, we know we have our complete message. So now with this particular array, which is message 40 with 12 bits, we're ready to analyze the data. At this point, we have an array holding message duration in ticks. So what we need to do is convert those ticks to microseconds by dividing it by 16, and next we have to decipher the data by dividing it by 600. If the result from our division is 2, then that message duration is equivalent to bit equal to 1. If the result is 1, then that message duration represents a bit 0. And finally, if the result is 4, then that message duration represents a star. So let's see how we do that in our code. So the first thing we do is we take the message containing the duration in ticks, divided by 16 to convert it to microseconds, and then divided by 16 to decipher the message. So as I noted, if the result is 1, then the message is 0, so we print that information into our laptop. And then after doing that, we store that duration in an array that I call a command, and then increase the counter. Next, if I go for this, for example, for a second time, and the result is 2, then that means that that data duration represents a bit equal to 1. Again, I place that 1 into my command array, which is going to contain the whole message, and I increment the counter. Now if it's a 4, then what I do is I send the message to the laptops, and I print an S, meaning that the is the start message, and then I put my a variable called S to 1, equal to 1, and I set my counter to 0. So basically what I'm saying, hey, if I get an S, that means that this is the start of the message, so the counter should be 0, the counter which is going to drive the command array. And then I go through the whole data. So once I've completed through the whole array, then I ask the question, hey, is there S equal to 1? That means that the start message has arrived. And then I ask, hey, and is the counter 12? That means that I have my complete message. So I have a start and I have my complete message. Then what I do is, well, the first thing I do is I set my start to 0, counter to 0, and then I calculate the whole 12-bit message so I can analyze it. So if I take the multiply the command 0, which is the most significant, by 64, because what I want to do is I want to get the 8-bit command message. So the rest I'm not interested. So I'm interested in the first 7 bits. So that's why I take the command 0 by 64, command 1 by 32, 16, multiplied by 8, multiplied by 4, and then multiplied by 2, and then multiplied by 1. So next, now I have the hex value of the whole command, and now I can print the command into the laptop, and then later on I'll figure out what to do with the command. So the main thing is that I got a message from the remote control, from the Sony remote control, and now I've deciphered the message and call it hex command, and I'm going to print it on the computer. So the idea is that we're going to see the actual message, which is here 0, 1, or start. So I print all the message in tab, and then I extract the actual command, and that's what I print here. So that's going to become much clearer when we see the actual output of the program and we go through the whole program. Let's start reviewing our program. So we have our typical header, and we have here a routine which initializes the input capturing. So we have we start with start capture in the folding edge. Then we enable the interrupt, and we set the counter to 0. Next, we have here the routines to enable and disable interrupts, and then we get to the main program, which is we have to initialize the UART so we can transmit information to the laptop. We initialize our variable inhibit to 0, initialize the capture, and then we start with the not rising initial setting of the edge, and we finally do the enable interrupts, and there is nothing else on the main program. Everything happens on the interrupt routine. So let's look at the interrupt routine. So as I noted before, we go in with disable interrupts. Then when we go into this routine, we don't know if the routine was triggered by rising edge or by falling edge. So we need to figure that one out, and what the parameter that does that is the edge, which can be not rising or can be rising. So to start, we did set up the edge to not rising. So when we come in for the first time, First thing we do is we store the current value of the timer in ticks. Then we change the edge from not rising to rising, and then we change the interrupt routine to trigger on rising edge. Next, we ask, hey, is the inhibit greater than 36? Now this 36 number was something that I picked as convenient. So what I wanted to do, this is going to define how many parameters we're going to have in our array of bits to analyze. And I decided in this case, the more the merrier, and having three messages to 12 bit each message. To have 3 messages would be nice, so we can analyze those 3 and compare if needed. So the first time we come in, we do not rising. Then of course the if statement are going to be true, so we get out of the we enable the interrupt and get out of the service routine. So the next time we come in, then we say if the edge is not rising, that's not going to be true, so we're going to go to the else, in which case we're going to again get the X, I should say to get the clock value, which is the ICR1, and then we're going to ask if the end tick is greater than the start tick, and we do that because we don't know if the counter has rollover. But in any case, what we basically want to do is figure out how long the message lasted. So we're going to subtract the end tick minus the start tick. Or we're going to do this operation, which is 65,536 minus start tick plus the end tick. And that's if the counter had rollover. So what we basically do is for each of the parameters, each element of the message 40 has the duration of a message, and basically we need to figure out if the message is a 0, a 1, or is a start message. So we go ahead and continue to increase the inhibit, and basically every time the inhibit gets to 12, we have one complete message. So the inhibit gets adding up here till we get to 36 to 3 messages, which would be 12 bit each message. We get 3 message, then we drop down to this. This if statement becomes true. So we have the message 40 with actually 36 parameters. So we get set our initial values of counter equal to 0, S equal to 0, and then we go for I 1 through 36. So what we want to do is we want to go through each of these parameters and figure out what is the value that it has. And as I noted before, if I take the parameter and divide it by 16 to get the microseconds, and then by 600 to get to figure out if the message represented a 1, a 0, or the start command. Now if it's like if it's a 1, then we know that the parameter we got represents a 0, and I'm going to put out the 0. I'm going to send the 0 to the laptop, and then I'm going to save this value in a counter, and then I'm going to do the same thing for I'm going to do that again till I get through the 36 parameters. And then so now as I go, once I'm done, then one of the 6 I want to know is if the S is equal to 1, that means that at least we had one start command, and then if the counter is 12, that means that I have a start command plus 12 bits, which is a complete message. So if I have that, then I want to go ahead and figure out what's the command inside that message, and the command is going to be the first 7 bits, starting from the most significant. So I will go ahead and calculate that by multiplying the most significant by 64. Then the next one I multiply it by 32, then by 16, 8, 4, 2, and 1. After I do that operation, now I have the value of the command, and then I go ahead and send it to the laptop so I can display it, and then I set the command to 0, and then I start over. Now I set it to 0, then the inhibit goes to 0 again, and then I enable interrupts, and then I'm out. So let's go ahead and look at the output of the program. Pressing button 1, command is 0. Pressing button 2, command is 40. Pressing button 3, command is 20. Pressing button 4, command is 60. Pressing button 5, command is 10. Pressing button 6, command is 50. Pressing button 7, command is 30. Pressing button 8, command is 70. Pressing button 9, command is 8. Pressing button 0, command is 48. So now we know what's the command for each of the keys that we press on the control remote. So what we're going to do is we're going to have to use this information to do something in the next program. So I know, so I'm saving the information, so I know that button 1, the command is 0. Button 9, the command is 8. Button 5, the command is 10. For 3, I get a 20. At 2, I get a 40. And so forth and so on, and 80, 70. So what I'm going to do next is I'm going to press a button, and I'm going to see if I'm going to decipher the information same as I did here, and I'm going to figure out what I need to do according to the program. So the next example, what we're going to see is that we have a switch statement where we're going to create a number of, we're going to light up a square depending on which button was pressed. So the remote control, which somebody's going to press a button, and we're going to turn on and off a particular item in the display. So what we're going to have is a case study, a switch for the key. The key is going to be one of these numbers. So when we get a 0, we're going to flash a box for button 1. Then an 8 is going to be 9. Then we're going to have for case 10, we know that we have to flash the key 5. Case 20 is key 3. Case 30 is key 7. And so forth and so on. So the idea is that we wrote a program, we read the data from the Sony remote control, and we capture the commands for every time you press a different number. And now we're going to write a program where we're going to use that control remote because we know what's the output and we know how to do something with that output. So let's continue with our presentation. Okay, so let's go to our sample program. So sample program, what we're going to do is first we're going to let's look at the setup. So we're going to have the IR receiver reading from the ATMEGA 328, outputting it to the ATMEGA 328, and then we're going to have the microcontroller hooked up to the display. On the display, we're going to draw a number of boxes with numbers, which are going to be similar in geometry to what we have here in the control remote: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 down here. So the idea is going to be that every time I press a button here, if I press a button 1, then in the display the number 1 is going to be light up. If I press number 2, the display number 2 is going to be light up. So and we'll know which button you've pressed, because on the first program we learned what were the commands associated with each of the buttons. So let's look at the problem statement. So a sample program to develop a display graphics that represent the remote control buttons from 0 to 9. Read the signal being transmitted by the Sony remote control. Decipher the signal using the data obtained from sample program 1. Like I noted, we know what are the commands associated with each button, so we decipher that, and finally we light up the corresponding button in the display. So let's go ahead and see how we do that. So I'll start by giving you an overall view of the program, and then I'll come back and get into some of the details. So we have a routine here to initialize the input capturing. We have a couple of routines, one to enable and disable the interrupt. Next we have a routine which I call the flash square, which is going to turn on and off the different squares of the display. We have a draw remote control. That's the one that draws the display that we're going to see in the shown. Next we have the turn on key, which is basically going to identify which key was applied by the user via the remote control. Next we have the main program that initializes whatever needs to be initialized. And finally we have the interrupt capture routine, which is going to do all the heavy lifting, you could say. So let's look at let's go and get in some of the details. So we have the input capture, which basically says the interrupt. So every time there is an input, external input, it captures it. We start with a falling edge, so as soon as it can sense a falling edge, then it's going to immediately capture the time when that happens, and then eventually we'll change it to a rising edge, and the time will be captured at that point. Next we have the enable and disable interrupt. That's nothing new here. And then we have what I call the flash square. What this is going to do is going to fill up the area of each of the buttons as applicable. So if the user presses button 1, then we're going to fill up the button that represents button 1 with a different color. So what we require here is basically the X1 and Y1, which are the lower corner of the square, and the X2 and the Y2. And then we're going to use the fill window area, which is that was developed early on in our first when I first introduced displays, and we're using the same routine without changing it. Next is also going to give us the number of the button. So the number of the button, each button has a number and it's being displayed. So here what we need to do is we need to convert the unsigned integer into a string. So what we do is we just use the itoa function, which actually converts the unsigned to a string and stores it in the str2 parameter. So here we fill up the area. Next we write the number that goes with that particular area. Then we basically bring the button to its original state and draw back the number. So this makes the button color change, and this brings it back to its original color. Then we have the draw remote control, and basically what that's doing is just drawing all the various squares that are going to represent each of the buttons in the remote control. And we use the draw square. Now the draw square, I explained how that works in presentation that was 36 and 35, where we do the graphics and also the magnetometer. So I'm not going to repeat it here. Next, we have the turn on key. So when the user presses the button, it sends a command to the microcontroller. The microcontroller has to extract the command and figure out which it is. And once it does that, it calls the turn key, which is the one that is going to decide which button was pressed. And once it decides that, then it's going to call the flash square routine, which is the one that changes the color of the button. So here you have the different case for 0, which represents 1. For example, 20 represents button 3. 48 represents button 0. 70 represents button 8. Next we have on the main program. In the main program we're going to initialize our ports, the SPIs, so we can communicate with the display when we're going to initialize the display. Then we're going to send a lot of our data to the UART so it can be displayed on the laptop for troubleshooting. So we have to initialize the UART. We have to initialize our input capture, which senses when the signal comes up, and then we always send our customary hello message. And to start, we're going to set this parameter to not rising, and we're going to finally enable the interrupts. But before we get completely out of the main program, we're going to of course fill up the screen with same color, and then we're going to write the hello world. We're going to draw our squares. So this area here, what it's going to do is going to ensure that we have a display that shows the boxes that are going to emulate our display. Now let's look at the interrupt. So we're going to get interrupt if we get a signal from the remote control. The signal can be either rising or falling edge. So we start by asking if it was falling edge, and then if that's the case, then what we basically do is we store the value and the start tick, and then we change the edge to rising, so the next time we're going to treat it as a rising edge, and then we change the capturing, so it's going to trigger on rising edge. So next time we go in again, then we're going to end up in the else routine, in which case we're going to store in the message 40 the actual duration parameter, and then we do the same thing, change the edge to not rising, and we store the data, and we increase the inhibit. Now when inhibit gets to 12, that means that we've gotten 12 messages. So what we need to do now is we need to take out information from those 12 messages. And this is, I'm just going fairly quick because it's same as what we did on sample program 1, except that this time we're doing something with the data. So the rest is same as program 1, except when we get to this point. When we get to this point, we're going to set our counter to 0, and we're going to send our variable s, which is going to signify start, to 0 also. So then we're going to go through our parameters that we have in our array message 40, I should say. So one of the things that I changed here from program 1 is that the duration of this signal, which is going to represent a 1 or 2 or the stop, they actually have a tolerance. So I had to add a tolerance here because after reading the literature, sending the signal from the IR, and the IR, I should say the IR transmitter and receiver, they have tolerances. So you have to account for those tolerances. So I decided that the one is going to be if the duration of the signal is greater than 400 microseconds but less than 890. So what I do in this message, I just divide this by 16 to convert the ticks into microseconds. And then up here is when I figure out actually what they represent. So we have 400 and less than 890, that's going to be a button 1 was pressed. If it is greater than 900 but less than 1950, then I say the button 2 was pressed. If it's greater than 2000 microseconds, then I know that the start button was pressed. Then according to this result, we're going to either say that the command counter was a 0, so I'm placing the whole command into this array. So either it was a 0 and then I increase the counter, or it was a 1, or it was a 4, which is the start. So that's based on these values. So once I've done this, then the next thing I do is I go ahead and break. Now if I don't get, if it's not a 1, 2 or 4, then I send a message saying, hey, parse that I was in the default area, so I know that I'm getting numbers that shouldn't be there, and then I have to troubleshoot it, which I already did. So I go around till I get my whole message. So once I've done with that, then I ask the question, hey, did I get the start message? Okay, so if I get the start message, that means now I need to get the first 10 bits. And so then I said, hey, I got the start, and is the counter greater than 10? If the counter is greater than 10, then I know I got the bits that I'm interested in at least. So with that information, then I'm going to figure out what was the command that I got. So I just get the most significant, multiply it by 64, then by 32, 16, 8, 4, 2, and 1. That's the same thing I did on the first program to figure out the command, what was the number. Then I send that command to the laptop via uint16, and then I send it to the turn 1 key hex command, which is the routine which is going to figure out what key needs to be turned on, and then I set everything to 0, and then I go back. So let me go back for a minute to this turn on key. So the turn on key here is the one that does, hey, what's the command? It's what button do I need to press? So it decides here, and then it goes to flash, which is the one that is going to light up the button that needs to be light up. So let's look at the output of this program. So here we are pressing the button 1, 2, 3, and we can see how the our receiver is getting the signal 5, 6, 7, 8, 9, and then the 0, and we have our hello world here. So again, I'm just pressing random numbers, the 8, and every time I press a random number, you saw how the remote, the receiver reacted to that command. So with that, now we can go to the next sample program where we are going to actually use a receiver and a transmitter. So at this point, we have characterized the control remote. We've shown that we can press buttons and light up the correct number on the display. And of course, what I'm inferring is that once I press a 1 here and I turn the 1 in this display, that means that I can do whatever I need to do. This is just an example of taking some tasks to get accomplished when the button gets pressed. Okay, so let's go through our Next, sample program. So let's look at the setup first. So we're going to have our same setup that we use for the remote control, which is the IR receiver. Here we have the microcontroller, and we have our display and our laptop. So the idea here is that we're going to, instead of using the remote control, the Sony remote control, we're going to have an ATMEGA microcontroller hooked up to a transmitter. And also we're going to be hooked up to our laptop. And the idea here is that we're going to try to put out the same signal as the remote control. So this setup received a signal and accepted signal for remote control, and then if we have done this program correctly, then this program should be able to simulate a remote control. So let's look at what the statement of the program. Okay, 1. Emulate the Sony remote control transmitter signal. So here we're going to have our display, and the idea is that we're going to turn on the different buttons on the display using this particular transmitter. Transmit commands to light up buttons 0 through 9 in sequence. So once we turn this on, what it should do is send commands to light up button 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 continuously. Next, no change to the receiver software developed for the sample 1 should be needed. So we're going to leave this portion exactly the same as we did actually from program 2, except that we're going to replace the Sony remote control with our own, I could say in quote, remote control. So let's see how we go about doing that. To transmit data over the IR, we're going to have to generate a 40 kilohertz signal. So let's figure out how we do that. So first I'll start showing the X and Y axis where I show the ticks versus time. Next I have the 0 to max for the counter that we have selected. And this line starts at 0 and over time is going to go to the max counter. Now to generate a 40 kilohertz signals, we need a period of 1 over 40, which is going to be equal to 25 microseconds. Next, let's look at the output from the controller as time goes, as the counter ticks. So we're going to have output voltage versus time, and then at this point I'm going to select the output compare value. I'm going to give it a value. Now we want our signal to have a cycle of 25%, which means that 6.25 microseconds, which is the 25%, times 16 times per second, which is the number of ticks of our microcontroller, that gives me 100 ticks. So if I want a cycle of 25%, then I need 100 ticks, which means my variable OCR18 needs to be 100. Now the time off is going to be 18.7, which is the 75% microseconds times 16 ticks, which is going to be a total of 300 ticks. So basically here we define the number of ticks for our 25 microseconds, and then the ticks that we would have for the 25% 25 duty cycle. So let's see what this means. So basically we're going to go 5 volts till we get to the output compare value, and then we're going to go to 0. Next we're going to start our cycle again after
25, we have to do after 25 microseconds. So what this means is that this the period, which is this line here, which starts at tick 0 and goes all the way to tick 400, that's 25 microseconds. So that gives us our 25 microseconds. So here, where I got the parameter for the program, is going to be ICR1 is 400, which is what the period needs to be, and then the OCR1A is going to depend in what the duty cycle. How did I decide the 25 what the duty cycle? Because that's what they say the signal should be if you're going to emulate the Sony protocol. Now, I just repeat it because of the 440 kilohertz. And then I need to use a non-inverting, and these are the values of my parameters so I can get this signal correctly. Now, there is nothing new here. I'm just giving you like a refreshment of the other things I have presented in the past. So this should be nothing new. So let's look at the code. So I'll go first through give you an overall view, and then we'll get into some of the details. So we're going to use pulse width modulation to generate, like I mentioned, our 40 kilohertz clock. So that's what this is, the initializing the output, our pulse width modulation, I should say. Then I have my this is going to turn on the signal, the 40 kilohertz. Now next routine, PWM off, is going to turn off the 40 kilohertz signal. Now PWM time on and PWM time off. So we know how to turn it on here and how to turn it off here. Now this is going to help us control how long we want this thing to be on and how long we want this thing to be off, because that's defined by the protocol. And then finally I have here the actual send the value of the protocol. So the bit is, hey, if the bit is 1, then we send 1200 microseconds, because that's what the protocol says. Then if it's 0, we send this 600 microseconds. And then after we send the on time, then we have to make sure we send the off time and it stays off for the correct time. So let's continue going through the this high level. So we have the send Sony 12 bits. So that's going to put together the whole 12-bit word that we have to transmit to the receiver, which emulates the Sony remote. And then in the main program, we're going to initialize whatever we have to initialize, and then we're going to send the codes to get the right buttons applied on and off. So let's look at some of the details. So here there's nothing new here, and basically we are just setting up the parameters, and I showed this is the duration of the signal. This is the time on, and then this is setting up the counter to be 0, and then we always start with the pulse width, turn it off. So to turn it on, we just get this the TCC R1A to 1 to turn it off. We do the same thing but set up to 0, and always, just in case, we turn off the PD1 to make sure there is no light coming out, just as a good way of doing things. Now the time on is basically we're going to get the amount of time you want on, so we turn it on, and then we do a while, and the while it goes around is going to be decrementing the value that we send. And every time you go once through this loop, you wait 1 millisecond, then you go around and the value gets decremented till you get to 0 and you got your time on. Now you do the same thing for your time off. So now let's send the how do we send a bit which is a 1 or a 0. So we come in here, and if the bit is, you need a 1, then you just put a 1 here, and then you have your pulse width. We send 1200 microseconds on, which basically gets here and it's going to get decremented on the on. Then after that, every time we send an on command, we need to wait 600 milliseconds off, so we send the off. So we're going to send the logic 1, we send 1200 milliseconds wait, or we're going to send 600 millisecond wait, and then no matter which one we send, we are always going to go ahead and wait 600, I should say microseconds. If I said milliseconds incorrect, it's microseconds. So let's see how we go about sending our 12 bit. So what I'm going to do is I'm going to send the first 7 bits, which is the command, and then follow by 5 zeros. That gives me my 12 bits, because I don't care. I only are interested in sending the correct command. The rest of the message, which represents the device, I will not send that, and my receiver is not going to look for that either. So I start with the pulse width modulation off. Then I turn it on. Then I wait for the on time of 2400 microseconds, and then wait for 600 microseconds. So what I'm doing with these two parameters is sending my start bit. So start bit 2400 on, 600 off. After I send my start bit, now I'm going to start sending my my command. So I take my data and get the first bit and transmit that one. Next, I shift everything to the left one of the data, and then I get the next one. So I go one by one till I've extracted all the bits from this data. Of course, if it's a 1 with the AND, it's going to stay as a 1. If it's 0, it's just going to turn into a 0. So that's how I send my 1s and 0 of the message. Now, once I've sent my command, which are the first 7 bits, so I send my start, I send my command, my first 7 bits, then I still need to send 5 more bits to complete my 12-bit parameter, and that's what I do here. And once I've done with that, then I just turn the pulse width off, and I'm done sending that particular message. So let's go to the main. So what do we need to do on the main? So the idea is I want the key number 1 to come off and on. I should say key number 1 to come on and off as I send this message. So every second I'm going to get key first 1 on off, 2 on off, 3, 4, 5, 6, 7, 8, 9, and 0 on off. So you're going to see my transmitter sending an IR signal to the receiver. My transmitter is emulating the Sony protocol. I did not modify my receiver, and the receiver should be getting the signals and turning on and off the signal accordingly. So let's look at the output. So here we go, pushing the buttons. You can see how the lights come on. So that's 7, 8, 9, 0, and then 1, 2, 3, 4, 5, 6, 7, 8, and you can see how the lights are flickering here, that the message is being sent. So what I did is I wrote a program to emulate the Sony remote control, which is driving this particular transmitter, which is driven by this controller, and then I send that signal to our receiver. That's the same receiver I use for reading the data from the Sony remote control. I did not change that code. I just left it, and I made sure that my transmitter was successfully emulating the remote control, which it does because we saw how the numbers went from 1 to 0 a couple of times, and every time I could have program it to go through any combinations. So with this, I think we're ready to continue with our program.
Okay, so this basically gets us to the summary. And today what I did, I gave you a description of receiver and transmitter for the infrared receiver and transmitter, I should say. Then I talked about the Sony protocol and showed you how it worked. Then I went to sample program 1 where we decipher what was the output from the remote control so we could characterize all the commands. Then sample program, should say 2, what we did was we took the remote control and we showed that every time a button on the controller was pressed, the display light up the equivalent number. And then finally we went through sample program 3 where we programmed a transmitter so it could send messages to the receiver that we had been using all along. So with this, I would like to thank you very much for taking the time to spend with me, and I hope I see you again. So again, thank you very much.